screen. Screen 2. I hope you can see my terminal with some code written in it. Yeah, I'm going to start talking a little bit about how and what zk applications are and how they work, and then I'm going to slowly move over to the PIL language that the Polygon Hermes team created to write their zkEVM, and then we'll talk a little bit about the PIL State machines that we looked into during our review. If you have any questions, please just interrupt me with audio. I think it's better if we get like a lot of questions answered right away, because otherwise you might just not understand what's happening later on. Yeah, so what do zk applications do? Like, why do they exist? I saw that like last week there was also a talk about zk applications and R. So if you were, so if you were there last week, you probably know a little bit already about what these applications do and what they're for. So one of the main applications is privacy. So let's say you have a computation that you want to perform. So for example, here I have a little program written in zkEVM where I have a challenge, this public element here called B, and then I ask here, can you give me 3 numbers so that when I multiply the 3 numbers, I get B? And you want to do that in a way that you don't reveal what the 3 numbers are. So the 3 numbers are private, and you're going to generate a proof that is going to prove to me as a verifier of this challenge that these 3 numbers multiplied do indeed equal to B, and without revealing what these 3 numbers are, so with zero knowledge. The other application for these circuits, like this one here and others, is what the zkEVMs actually use the circuits for, which is scalability. So as zk snarks or starks and all these proof systems, they have this compression property besides zero knowledge, where they can basically generate a much smaller proof than the computation itself. So if you want your Ethereum smart contract, for example, to compute some heavy function, and then you're going to spend a lot of gas, instead of doing that, you can do it off-chain using these circuits, and then only submit a proof that you computed that function correctly, and then you know the answer for it. That's what the zkEVMs do. They generate a proof, they generate an off-chain proof that a certain transaction modified the state in a certain way, and then only the proof is verified on chain by the contracts that the zkEVM teams have written. So I'm going to start with a small example for people who are not familiar, or even if you are, it might also be just like a refreshing piece of code. So this is the zkEVM code. You can write the same thing in Nora, Circom, and other high-level languages. So basically, again, what we're doing here, we're taking 3 numbers that are private, that only the prover knows, and a challenge B. And so me as a verifier, as the challenge maker, I'm writing this program here where I have an accumulator, starts with run, and then you're going to multiply the 3 numbers over with this accumulator, and then in the end we will accept the answer only if it's the same as B. So I write the circuit as a verifier, and I'm going to compile this circuit. All right, so you see here it says number of constraints 3. What does that mean? So zkEVM is the main encoding, the main proof system that zkEVM uses Graph16, and the arithmetization that this proof system uses is called R1CS, which has quadratic constraints of the form A times B equals C. So it has a bunch of these. So zkEVM basically compiles this program here to a bunch of different constraints. And the constraints it compiles to is basically this here. So you can think of this as kind of like the assembly or the intermediate representation language for these proof systems, because these are going to turn into polynomials inside the proof systems. And then the cryptography is going to happen over those. So what we can see here Let me close this. And yeah, so effectively this compiles to this loop's going to be unrolled. And what we have is, so we have a private field 0, 1, and 2, which are A0, A1, and A2 in the array. And then you have 3, which is the public B. We're going to unroll the loop. So we're basically, our accumulator is going to be 4 here in this case, variable 4. So we're going to multiply A of 0 and A of 1. That's going to go into the accumulator, and then you're going to multiply the accumulator with A of 2, and that's going to go into variable 5. Then we're going to compare variable 5 with variable 3, which is our B variable, and this must pass. So all these constraints here. So what this is going to become is just a single set of global constraints, and all of them need to be true when you pass values for all these little things here. And the way we do this is we compute a witness, and what this witness is going to do. So we can compute this witness, for example, passing all these arguments. So this here we're basically passing the 3 elements in the array, and the multiplication, the result. So it's going to be 6. If we compute it, says it wrote the value, the results of this witness file. And when we open it, you see that it has a value for each of these variables. And it includes values for each of these variables, including including the intermediate variables. So remember that our our API basically variables were 0, 1, 2, and 3. So this is A of 0, A of 1, A of 2, and A of 3, and B, sorry. And this 4 and 5 were this like accumulator things that were inside the function. And so we need to also compute value for these. So the witness generator, what it's going to do, it's going to take, so this would be you, and as the challenger would be running this here. So you're going to take your private input, which is this 1, 2, 3 here, with the public challenge that I gave, which is the 6, the number I'm trying to factor. And you're going to compute this witness, which is just an intermediate step. After you have this witness, you have to make a proof out of this. And so first I need to run the trusted setup here, which is going to make a verification key and a proving key. I'm going to give you the proving key. It's going to be a public thing. And then you're going to generate a proof after computing the witness. So now we have this proof. And this is what the proof looks like. Just a couple points in a curve for this public input, which is my challenge 6. That's it. That's all you need. At this point, you're going to give me this proof, and notice that this proof says nothing about the numbers 1, 2, 3 that you had at first. Those are private. There's nothing here that points to the 1, 2, 3, so they remain private. At this point, you're going to give me this proof. I'm going to use my verification key, and then verify your proof, which passed. If I try to generate, if I try to use a different witness, so for example, if my challenge is still 6, but then I say 1, 3, 5, then the witness computation is going to fail because we can't make the circuit, we can't make all the constraints pass with these values. It's just not going to work. So this is basically the workflow. That's all. This is basically the workflow of some off-chain computation that you might want to do, and then in the end you get a proof that someone is going to verify either on-chain or off-chain. So what we can do, for example, is also export a verifier, and this is going to give us a Solidity verifier that we can deploy. And here we have this verify function, which basically takes the same inputs that I just ran outside, so that you can verify this on-chain. So if I have this, so if I deploy this verifier, you can take this proof that you just generated and send it to me on-chain, and my contract is going to verify if your proof is correct or not. And that's the entire flow. So we build a circuit, I build the keys, then I'll send you over the proving key, or it's going to be a public thing. You take your private witness, computer proof, send me back the proof, and then I'll use my verifier to check if your proof is correct or not. So this is a very basic workflow, and what we also saw that Socrates uses this R1CS arithmetization, which basically encodes your zk program into a circuit with a bunch of global statements. There's a different type of arithmetization though called AIR, which is used by Starks, and its concept is what's called an execution trace. And the difference is that instead of seeing the program as a global set of constraints, we see it more as a state machine, kind of. So we see it as a transition function. So the same program, we could see it, you'd see it as a table. So this is our execution trace for a computation like this. So imagine that we have 4 rows 0, 1, 2, and 3, and we can give each of our variables a column, and then our transition function defines a constraint that needs to be true for every pair of rows, including the wrapping pair. So we always talk about the current value of a column and the next value of a column, so ACC prime here. So when we're in the last row, ACC prime is actually the first one, so it wraps around the whole table. And this would be one way, for example, to define the same program using an execution trace. So we have our same A, we have our B, and we're going to load we could use 3 columns for A0, A1, and A2. This is just a different way of writing it. Instead of using 3 columns, we're going to use a single column for A, and we're just going to load the different values you want to multiply in different rows instead of using more columns. So first we're going to load our 1, and then our 2, and then our 3. So this is going to be part of the witness. So this is a committed column. This is also a committed column. We're just going to load our 6 forever. So it's going to stay 6. It's our public challenge. And the accumulator, it's also going to be a committed column, which needs to obey the constraint that it multiplies with A. And we need a kind of like a helper constant column here called isLast, because this transition function, it changes when you're done with the result. Because what we want to do is, when we're done with the multiplication, when we have multiplied all the elements of A, the result must be in ACC. So at this point, ACC must be the same as B. So how do we know we are at this point? Because we don't know in which row we are. We only know we're in a certain row, and we only have this row and the next. So we define this constant column here, which does not depend on any witness, does not depend on our input or anything else. It's called isLast, and it's 0 everywhere except the last row. And this allows us to write the verification bit here, which says when isLast is 1, we want ACC to be the public challenge B, which is what should happen here. When isLast is not 1, we want the next ACC to be the current ACC times the current A. So this will take this and multiply and put it here. And then we'll take this, multiply, put it here. We'll take this, multiply, and put it here. So these constraints need to be true for every row or every pair of rows, if it also refers to the prime version. And this is what PIL does. So PIL is, it means polynomial identity language. That's a language that the Polygon Hermes team created to aid their own development of the zkEVM. And if you write the same thing here in PIL, this is what we have. So we have a namespace. So any questions so far? Cool. So I have a namespace, the same thing as a module. And here we have to say how many rows we want to use. And this entire thing here is the definition of a state machine, which you can also call from the outside. You can compose, you can do different things. And this is used a lot in their zkEVM. And it allows you to basically make things more modular and write specialized behavior with these low-level constraints here. So we have 4 rows. And here we're saying we're going to have one constant column, which we just talked about, and 3 committed columns. What are these committed columns? They are values that depend on the input somehow. And this is our main result check, which, so here we don't have like implications in ITEs, but this, if you look at this as like an arithmetic way to do an ITE, this means whenever is last is 1, then ACC must be equals B. And you see that if is last is 0, then this whole thing will also be 0. The constraint passes, but we don't care about the result. We don't care about the relationship between the accumulator and B when we're not in the last row. Let me just actually copy this over so you can see it at the same time. Yeah. This here is doing the other part, is doing this bit here. So when is last is not 1, we want the next ACC to be equals the current A times the current ACC. And this is defined over here in an intermediate polynomial, which you need to define separately because all of them have to be quadratic. And 1 minus is last is like a Boolean negation for values that are known to be Boolean. Yeah, looks nice and neat. We can compile this with wait, I was just PIL, yeah. We can compile this. It gives us a JSON file. That has a bunch of information about it's basically the compiled version of this PIL. It has all the columns, it has the number of constant, number of commitments, the degree of each polynomial, and so on and so forth. But what can we do with this now? So if we want to do the same thing as we did before, we need to make a witness out of the input. But PIL, it requires a binary format for the constants and the witness, and this is already a difference from what we saw before, because here we have this constant thing, which we didn't have before. So, and this is heavily important for the constraints to be true. Does anyone see a potential problem here related to is last? You can guess whatever. Okay, we'll keep it open for now. Yeah, so we need to generate this. We need to give values for this thing. So basically, the values we want are constant. We want to give these values here, 0, 0, 0, 1, and the way this is done for PIL and for the state machines in the zkEVM is by, you have this function called build constants that basically, yeah, builds that thing. And then here we're saying we have 4 rows. And then if we are in the last row, it's going to be 1, otherwise it's going to be 0, which is exactly the 0, 0, 0, 1 behavior we wanted for this. So now we can run yeah, we can generate our constants, which is just a binary file. And similarly, we need to now execute over inputs. So, and this pretty much does the same thing as we did before, just like taking the circuit and taking some inputs and filling out all the cells we need in the table, or all the variables we have in the constraint system. So here we're going to take the polynomials and the input, and the input is going to be A0, A1, A2, and B, and we just basically do the same thing. We build the entire table based on the inputs. So A0 is going to be the input 0, and so on. The last A we don't care about, so let's just write 0. and B is just going to be the same throughout the whole thing. And the accumulator is going to start with 1, then we do the previous accumulator times the previous A 3 times, and then finally our circuit needs to return true if the final accumulator is the same as B in that cell on the table. So now we can also run this. Okay. Now we have our commitment values, which are the witness. And at this point, I think we're ready to run the verifier. Yeah. So now we can run, we don't have a proof yet, but we can run the verifier that basically already checks if the witness fits our execution trace. And for that, we call the verifier with the commitment, with our state machine here, and the constant we generated for it. And it says that it passes. So if you generate a proof from this, you need to connect to a proof system, and this is not connected to a proof system yet. This is just the PIL compiler. They have a repository called PIL Start, for example, which you can generate proofs for this, but it's a bit more convoluted, so we're not going to get there. Just wanted to show that our execution trace is valid. We basically built this here, right? What happens though if we build anything here wrong? Is it possible to get a proof for something that shouldn't be allowed to be in a proof? Well, it depends. So the constraints feel like they're right. I don't think there's a problem here. But what about this constant here? It needs to be part of the entire workflow. Otherwise, because here inside the state machine, we're basically trusting that it's binary, right? Because this here and this here assume that is last is a binary number, whereas these are just field elements using some order that the backend is going to choose. So if you want to be extremely certain here, you could add a constraint that says that is last. What was the constraint? The binary constraint again? Is last square. Yeah, equals. Yeah. So basically here we're saying that is last square equals is last. And this is only true for binary values, right? It's true for 0, it's true for 1, but it's not true for all the other numbers. But we're not doing that here. We're basically just trusting that our constant is last is actually binary, which when we generated the constants here, it is binary, right? If we change it to something that's if it's just once everywhere, as you can see here, we can try to run that. So we have the constants, we try to run the verifier. It doesn't accept it. It says that some identities don't really pass, which is a good thing. But this is something to really watch out for. In fact, one of the critical bugs we found in the state machines was actually one of these constant polynomials that was supposed to have a certain shape, a certain pattern, but it had a different pattern that actually allowed you to manipulate the input value so that you could have some memory alignment that would actually, you could have some memory writes in misaligned memory that could let you write some different values. And it's a more complicated example to show everything, but the analogy is basically this. Imagine that this constant here was actually, I don't know, it had like a 2 in here. And maybe this lets you run an exploit on it, maybe not, but it's definitely not doing what it's supposed to do. Yeah, any questions? All right. So yeah, this is the basics of PIL. And I'm going to show the one of the state machines from their zkEVM. So the one that I want to show is the memory state machine. And it's a pretty cool one because it has it's a bit more complicated than the example that I just showed, obviously, but it's not too complicated. And it's pretty well explained in the, all the state machines are pretty well explained in the Polygon zkEVM documentation if you want to take a look and try to analyze it yourself. But we can quickly go through this. So this is the memory state machine. What does that mean? It means that it has a bunch of this commit polynomials, which you can see these as kind of like, imagine the memory state machine is like a separate little chip that does all the memory access. And it can be called by what is called here as the main state machine. So if you look for mem, that's something here. So here we have our memory access. So this is where the state machine is used in a lookup. So what this means that if this is a memory operation in the main switch, which checks what kind of operation things are, then we want this, the internal mup from the state machine this here, to also be 1, and it should be binary, and then all of this here should be associated to all of these here in a lookup. So this is the address we're looking into. This is a time step. And this is basically every time you execute an opcode in the EVM, you have one more step. It's not the program counter of the opcode itself. It's just you can see the step as a time. So it always just goes up 1. It's not about jumps, it's more about time. And this here is whether it's a write operation, so it's going to be true for writes and false for memory. For reads. And here the values. 3. So here I have 8 values, 32 bytes. So I have 4 bytes in each of these array elements here. So this is how the main, kind of like the motherboard of the whole thing, or the ROM here in this case, uses the memory. And inside the memory, there are a few constraints, and it's quite nice to see how it works. So, for example, we can see here that so this is the Boolean constraint. Yeah, exactly. This is another way to write the Boolean constraint, which is, the number times the number minus 1 is 0. So this also only works for 0 and 1. And this here is basically an implication saying that if mWrite is 1, then mup needs to be 1 as well, because you cannot have a write if it's not a memory operation at all. So these are all just like arithmetic ways to encode all these relations. It's going to be a write if the next step is a memory operation, and the next step is a write, so it's looking to the future. So it's going to be write in the future. And this is saying the read is going to be the same if it's not a write and if it's not a last access, because it has a big table for the memory itself. And the read is going to be different. I mean, in the return is going to be different if it's a write. The cool part here is actually these constraints here. So what this does, maybe I can actually show the memory state machine from the docs. Just give me 1 second. Yeah, so this is the Polygon documentation, and this is the memory state machine, and you can see that it looks pretty much like the example we had before, right? An execution trace has a massive table, and this actually has 2 to the power of 21 or 22, if I'm not mistaken, rows. So it's a pretty big table, and each of those polynomials I just showed, they're going to have a column, each of them. And we basically, all these constraints, what they encode is like, how do 2 consecutive rows interact, or what needs to be true for a single row. And the way this works is that each memory access, all the memory accesses are sorted. So it's not like sorted by time, it's sorted by address, because this is not really executing things. It's more about verifying that the memory accesses are, they conform to the EVM access. So the way this table works is we're going to sort all the memory accesses by the memory address that is being accessed. So here we're going to have all the accesses for the address 2, then all the accesses for the address 4, then for 6, then for 7. This column here, it's 1 for every row except the last, because we're going to have a different rule for the last row. This is the time step, so notice that this is not sorted globally, but it is sorted inside of each individual address. So this table is sorted by address and then step. If the address is the same in 2 rows, so here 4 and 4, then in the step column, this value must be less than this value. Strictly, it cannot be the same. And then you have like whether it's a memory operation, and then whether it's a write, so here is a write, here's a write, and here's a read, and then write with write, and so on. And this column here says whether this row is the last access of that address. So you see that here it is. This is the first access of that address and not the last. This is the last, not the last, not the last, last, not last, and this is the last. And what you want to do with all of this, you want to now write the constraints that are going to guarantee that everything that I just mentioned is correct. So this here, it says that if it's not the last access of a certain address, then the next address must be the same as the current one, which is basically for every 0 in this column, the next address here must be the same as before, which makes sense because if it was the last address, the last access of a certain address, it may be anything, the next one. It has to change. This one here is just saying that the last access is a Boolean variable, and this one here, this is a lookup, which I didn't really get into, but basically what this constraint here, it says is if it's not the last row globally, so if we are in one of these things here, then this is the constraint that basically says that it's sorted by address and then by step. So if it is the last access of a certain address, then this value here must be in this INCS column. And this INCS column is basically all the possible numbers because step can be 0 up to n-1. So we just sum 1, so it can be 1 to n. So translating to our natural language constraint, basically what this is saying is that if it is the last access of a certain address, then the next address must be strictly greater than the current one, which you see basically also like it doesn't only change, but it needs to be greater. So when we see a 1 here, the next address must be bigger. When we see a 1 here, the next address must grow, and the same thing here. So this guarantees that the first thing we're looking into is the address. If that's not true, this whole term here is going to be 0. And that leaves us with the next step minus this step. And this is a time thing. That's when we see that the inside of when an address is the same, then we're sorting by step, because then this step minus this step must be greater than 0. So again, strictly larger than the previous one. Questions? Right. Yeah, so I don't want to get too much into the more complicated state machines. I think this is a pretty neat self-contained state machines that allows us to see how things work in the constrained world. Also, when looking into the state machines, which only deal with this transition system 2 rows at a time sort of thing, there are different state machines that deal with 32 rows, for example, just 2 at a time with different selectors and so on. But this memory one is a pretty nice one. And we did manage to prove a few correctness things about these constraints, because again, when you're just looking into these constraints, maybe you think, yeah, it looks fine to me, but there's like a certain edge case that you didn't think of, and then your whole system ends up being under constrained, which means that effectively you can have a silent bug. So basically that allows may allow an exploiter to find a proof that the verifier will accept, but actually that would lead your system into a state that is not really desired according to the specification. And the tool we used for some of these proofs called Pilspector, what is here? This is correctness. Get rid of it. Yeah, so this tool here, we developed it the first 1 or 2 weeks of the review, and it allowed us to do some analysis using some sort of semi-automated analysis, like translating things to an SMT-lib encoding, and then calling SMT algorithm to different types of queries that we actually wrote manually. So one example is, again, taking our, let me see if I have PIL files here. No. If I take our, multiplication PIL that I started with, this is how we could call it with this SMT command. So we want to dump the query. We want to have 4 rows unrolled, because our use case requires 4 rows, right? Because we need to accumulate the multiplication. Our input variables are the A and B. Our output variable is the ACC, and this is kind of need to do because state machines, they don't always have a clear separation of what's input output, is more relational. In this case we do, so it does help the SMT queries. And here the PIL file we want to analyze. And what this tool is going to look for is nondeterminism in SMT, which translates to potential under constrained variables and potential exploits in the PIL file. So it says state machine is deterministic. It's actually a surprise. I thought it was going to be non-deterministic at first. But yeah, this is good. So we know that we don't have this non-determinism bug, and this right away gives us that assurance. And we can take a look. So this is what it looks like in SMT. We have a bunch of these definitions. These are a lot of the constants that we had during the review. These are constants from a lot of different state machines. And we basically encoded all of them in the tool itself, so we would have direct access to them. The query itself is, oh wait, why is this saying not true? Okay, yeah, the demo was going fine so far. Wait a minute. Polygon mol PIL. Get rid of this. This looks correct to me. It does this if there's no out. Oh, right, because I changed the namespace from global to mol. Okay, so now the result that I expected, it actually says state machine may be non-deterministic. So you have to look into the counterexample, and it has some weird stuff. It says that like row 1 is -2, which is definitely weird. And it says that is last row 3 is 0, which is definitely weird. Because is last row 3 should be 1. But then we also get this where is the thing? Here, the tool is telling us the constant is last using constraints has no lookup function. So we're actually not telling the tool what this is last thing is. So we gotta do that. So let's do this. Okay, so now we actually have a query. So basically what this whole thing is doing is actually we also want to do, we want to start at row 0, do this, and then go increase the rows. This is just like linking, for example. So what we're doing here is building 2 execution paths with the same input variables. So here we're saying a row 0 is the same in execution 0 and execution 1. And then what we do later is say that this would just connect ACC prime of row 0 to the normal ACC of row 1. So we just link all these prime variables. Then we apply the state machine over each row and all these variables twice. So we do execution 0, then we do execution 1, which is going to give us, in the end, the output we're looking into is the ACC of row 3 execution 0 and ACC of row 3 and execution 1. We executed the same thing twice over the same inputs. And now we're asking the solver, is it possible for these things to be different? So this is basically how we query for nondeterminism. We run the same thing, but we try to come up with different outputs for the same computation. And that's when the solver says, sure, it's possible. And it gave us some weird values that we're not convinced about. And this is basically how we would represent this is last function. So we have a relation between the row and the value, and it needs to give us true if the value is in that row, otherwise, or false if it's not. And the way we encode this is if the row is 3, so if it's the last row, the value must be 1, otherwise it must be 0. That's all. And then we also need to use this constraint, actually, I don't want to call it global. Mol. And then we need to use this constraint in the state machine. And this is also not global. This here looks good. All right, so now we can try again. But now we modified the SMT file directly, so let's just call the SMT solver directly. Oh, it's missing a query at the end. Right, it says unsat, which it's saying it's actually safe. This actually represents a proof that our system, when encoded with these constraints, it is deterministic, it's fully deterministic. So we don't have this under constrained bug. And just to show that again, if you remove that constraint from the state machine, which the tool complained about before that we hadn't encoded, then it gives us SAT, which would be the unsafe case when non-determinism is possible. And yeah, we ran this tool in a bunch of the state machines, but mainly the memory one, because the more complicated ones, it was kind of hard to run the tool. Yeah, we didn't have enough time to polish it too much to be very generic, but we did tailor it for a few state machines, like the binary state machine and the memory state machine. So yeah, it was cool to get some of these correctness proofs for some of the state machines. Yeah, that's kind of what I wanted to show. So like not too deep into the state machines, because it actually takes quite some time to get used to the specifics, and I feel like yeah, a lot of people would be lost, but yeah, happy to take questions now. Thanks. A lot of the issues we had when building the tool was that the state machines they can be quite different from each other in the sense of let me actually pull this into here. So this is the official repo of the zkEVM state machines, and the binary state machine, for example, it requires so this is a generic state machine that can compute different binary operations, like addition and multiplication and different things in the same state machine, and it requires 32 rows for a single result over words of 256 bits. So this is a big window. It can be pretty hard for solvers, can also be pretty hard to model. And if you go to memory, for example, then it only kind of requires this window of 2 rows. It's also parametric over this kind of like runtime window of when the address changes. So this is already very different from the binary one. So the other difficulty is also these constant polynomials, like what we see here. Them not being defined in PIL itself was a challenge because they're all defined in JavaScript. So we had to go to JavaScript code, which we did during the review anyway, to see if the constants were built correctly, and then just kind of like build versions of those constants in Rust for SMT. So that was also quite time consuming. And to improve upon the tool, I think it's not really a matter of I don't think it's too hard to improve. It's just time is needed. I think we just didn't. Yeah, no one is really working directly or full time on this, but I think it can be improved a lot without too much work. Okay, there's a few questions. I can go through them. Yeah, I think there were quite a few optimization ideas that should be in the report. I think it's easier to read in the PDF than going through the code. There was also one related to the binary state machine. I think this is probably the old version. Actually, I think it's this one here. So actually, this is another one of the critical bugs we found in the state machines. In the binary state machine itself, the cin variable was not constrained at first. So this led to a pretty neat, nice exploit that would let you prove that something like a plus b actually gives you a plus b plus 1. So you could always add this plus 1 with the starting carry in, and the verifier would just accept it, and you would see nothing complaining about it. And you can imagine the implications of basically having an add in the EVM actually adding 1 to it. So, and I think this was a suggestion we came up with. Basically adding this constraint here as a security constraint on actually making sure that the cin is 0 at the beginning of the computation window. The tool is already released. I can quickly paste it here. It's on Thibaut's GitHub. It's still kind of experimental, of course, but you're welcome to use it. Any reason why Z3? No, in fact, it's actually, the tool itself doesn't really care about the solver. You can actually choose which solver runs by default, if I'm not mistaken. Let me check this. Yeah, you can actually choose the solver you want to run. The default is Z3, but it also works with CVC4 and CVC5. In fact, I ran both CVC5 and Z3 every time when I was making these proofs. Thanks for having me.